Thanks, Edston. I think next time we need to cut my bio by half and add one for you. So let's do that next time. Um, Welcome everyone. I'm currently in Europe, and Edston, my colleague, is in Sydney, Australia, which is where our head office is. But it's great to be in Europe. It's a better time for me on this call. So the contents of today's presentation on submarine power cable current rating calculations. I'm going to talk about the fundamentals of current rating calculations, submarine cable design, bonding of submarine cable systems, how to model submarine cables. I'll talk about armor loss calculations and the critical sections for particularly for an offshore wind farm installation, including the landfall, the J tubes, and the seabed. I'll briefly mention the 2K criterion and dynamic ratings, and we will have a couple of calculation examples using our submarine installation method in our software and a J-tube installation. I will finish with some conclusions and recommendations, and then we will have a question and answer session at the end for around 10 to 15 minutes, depending on time. So please post your questions in the chat. Let me just allow the last few people to come in. ELEK cable HV software is used for the modeling, for the calculations explained in this technical webinar. It supports a very wide range of installation conditions that you can see along the top there, including the finite element method. It complies with IEC 60287 standard, which is the main standard for current rating calculations. And it can also model custom cables, including submarine cables, which are quite complicated, which I'll show you. And it's fully validated software with CGRADE Technical Brochure 880. You can download a free trial by requesting that from elek.com. IEC 60287 is the penultimate standard. It's a series of standards used for current rating calculations. It's commonly used. It is adaptable to common cable types, including modern types, not so much submarine cable types. It needs to be modified for submarine cables or extended, but it's still used, reliable, accurate, consistent, and provides comparability between different vendors providing different ratings. There are 9 parts to that standard. It's really quite complicated to implement. There's a lot of ambiguity in the implementation and the equations. And of course, there are a number of installation conditions, including subsea and in water, etc. J tubes they're not covered by the IEC standard. CGRADE Technical Brochure 880 is a great document for validating the fundamental calculations from IEC 60287. It's used for verification purposes in accordance with the IEC standards and the current best practices for these current rating calculations. Our software has full matching results, completely matching results to the maximum accuracy possible of 11 decimal places with all of those case studies. Another useful technical brochure that I'll refer to, it's particularly useful for three-core submarine cables or armored three-core cables. This allows or provides more accurate calculation methods for these armor losses, and the overall result is an improvement in current rating of around 10%. You can hear me okay, Edson? Yeah.
Yeah, okay, yeah.
Yep. Let's talk about submarine cables design or the cables themselves. Typically, the conductors are copper. However, some projects use a combination of copper sections and aluminium sections. Especially for deep water installations, aluminium is used because it's lighter, so less weight during installation and retrieval if that's necessary. Typically, in modern submarine power cables, we are using XLPE as the insulation for AC and DC applications or cables. There are dry type cables, submarine cables that are more complicated, more expensive. Those typically have a welded sheath, watertight metal sheath around each core. You can see that this in the photograph. There's a red arrow pointing to the solid welded lead sheath, which is watertight. Another type of design is a wet design, which doesn't have the solid sheath. These wet design cables are typically used for the inter-array cables of wind farms, and the dry type or dry design cables are used for the export cables of higher voltages. So that's about the sheath. Lead is commonly used. There's a bit of a predicament currently in Europe. It's expected, or there's a real possibility that lead will be um, regulated in Europe, and it may no longer be allowed to be used so readily in cable systems, especially. So that's going to be interesting. Now, these submarine cables are armored cables. There's either a single layer of armor. So you can see in the picture here, you've got a single steel layer of armor. That's usually galvanized steel. However, if it's stainless steel, this has the advantage of being non-magnetic, which means you have lower circulating current losses and eddy current losses in the armor, which can be significant. I'll show you on the next slide. Stainless steel grade 316 is recommended. It's very, very expensive, however, and it's common that 304 grade is used instead. The outer serving is something interesting. It's typically a polypropylene yarn. The bonding, we need to mention the bonding of these three core submarine power cables as well. Due to practical reasons, these cables are solidly bonded at both ends. Therefore, the disadvantage of that is that you have circulating currents within the armor and the sheath. And you can see an example here, a 30 kV submarine three-core cable with a lead sheath, I believe, lead sheath around each core, uh, and solidly bonded. You've got 900, a rating of 920 amps for the phase conductors. And then as a result, you have a sheath circulating current of 85 amps, which is not as high as a single core cable. However, it's relatively significant. And the flow of such circulating currents results in a derating of the three-core cable. But in general, three-core cables have lower electrical losses than single-core cables. That's one reason why they're predominantly used in submarine applications. So how do we model a submarine power cable? When we're performing current rating calculations, we need to model the submarine cables from a manufacturer data sheet. Uh, we have to obtain one of those. And typically there'd be a diagram. It may or may not be so accurate. And you can see on the right-hand side, there's a sort of a table where each of the layers in the cable, each of the objects in the cable is defined. The material is hopefully defined, properly defined. There's a thickness which leads to a diameter. And the OD, or outer diameter, of each of the layers is usually defined in the data sheet. And hopefully all of the layers are properly defined. There are so the requirements for modeling a, a submarine power cable are that we need its construction, we need the material types, the material properties, and we need the dimensions, the thicknesses of each of the layers. There are certainly challenges, especially with three-core submarine power cables. We have modeled a lot of these, and very often there's incomplete information. Uh, sometimes, mm, sometimes you can use back calculations. So if you know the dimensions of one layer, you can sort of back calculate the dimensions of another layer, which is useful. Sometimes we need to combine layers uh, in terms of materials and thicknesses. There are very often properties such as lay length factors of the conductor or the armor that are not almost never provided in the data sheet. And even if you go back to the manufacturer, it may be difficult to get some of these properties. But I provided some standard lay length factors here that you can use. You need these lay length factors for calculating the electrical losses, the circulating losses. It's a good idea when you model the submarine power cables from a manufacturer data sheet just to do a sanity check of the current rating. So usually on these manufacturer data sheets, there's maybe a couple of current rating values for some sort of installation. You know, if it's buried, uh, the data sheet may say buried at 1 meter in such and such a soil, and the ambient temperature is such and such, then we say the current rating is this. Now, we don't know how they've performed the calculations, whether they're doing fully compliant IEC calculations. They're certainly not measuring it. They're using software. They're using software, either our software or something similar, to calculate the rating. It's a good idea once you've modeled the cable to do a sanity check calculation and just check that you're in the ballpark, because these calculations are very sensitive. If you get a material type wrong, if you get a thickness wrong, it can very much affect the current rating. So we've got to make sure that the model is correct. So we can do that by doing some simple calculations to match the data sheet ratings. We can also try and match the AC resistance. So very often the AC resistance is given on the data sheet, and using the software and adjusting the properties, the parameters, we can of the conductor, we can try to match at least match the AC resistance of the phase conductors, because then we are more likely to have a closely matching current rating with the manufacturer data sheet. Here's a very brief video which shows you in the software. There's a three-core submarine cable. I must correct this. It's not a 400 kV cable. It's actually a 220 kV three-core cable. So on the left-hand side, you select the layers that you have. Now, in a three-core submarine cable, it's very common to have that you'll need to add custom layers to the model. So you add the layers on the left-hand side, and then on the right-hand side, you go through each of those layers and you enter the properties such as the conductor size, the conductor dimensions, the conductor material, the skin factor, skin effect factor, proximity effect factor, etc., etc. You need to go through all of the layers and enter the material types and the dimensions and the properties, including the armor. And then finally, the outer jacket. So we've got to have a matching model there. And then once we have the matching model, we can use that to model the installation and get an accurate current rating value. Okay. Let's talk about the filler of the submarine cable. So they use special profiles. This is not your typical three-core cable. So you'll see a couple of unique things about the submarine cables. So there is typically a jacket, an additional jacket around each of the cores. That's the first arrow on the left. There's a thin insulating jacket around each core and around the sheath. And then you have these profiles, what are called profiles. That's those plastic frames uh, uh, that are holding the cores of the cable together in this trefoil triangular arrangement. Now, there's when the cable is dry outside of the water, it's those gaps are filled with air. When they're in the water, they're filled with water. But typically for the modeling to IEC 60287, that those air gaps or the water gaps are ignored or assumed to be actually insulation. We need to talk about the magnetic armor loss calculation. So when you have especially magnetic armor, there are higher losses. So the magnetic armor actually causes additional losses in the main conductor, in the phase conductors. Now, this is accounted for in IEC 60287 with a simple multiplying factor of 1.5. That's in the top right-hand corner. You'll see that equation. So that 1.5 multiplying factor affects the skin effect factor, YS, and the proximity effect factor of the conductor. It's a very simple approach and very conservative. And there's been a lot of concern in the industry, especially the wind farm industry, that these factors were simply way too conservative and resulting in smaller cables, larger cables than necessary. And in the bottom right-hand corner, actually, the magnetic armor actually also has an impact on the sheath losses. And again, that's accounted for with this 1.5 multiplying factor as part of IEC 60287. Then we had C-grade technical brochure 908 because of all this concern by the wind industry and especially the manufacturers. They were suggesting, and there were several papers on this, that the 1.5 multiplying factor is conservative and that there should be a working group should be developed and better, more accurate calculation methods for armor losses should be developed. And that was done, and that was recently done and completed in 2023. And now what we see is improved current rating calculations for these three-core armored cables. In our software, we have implemented the methods recommended. We need a little bit more information about the armor, such as the lay direction and the relative permeability of the armor. A couple of more inputs. But overall, we can approximately get an improvement of around 10% in the current rating of these submarine power cables using this method of armor loss calculations. Here's an example of that methodology being applied. On the left-hand side, you've got this three-core submarine cable, again 30 kV submarine cable that's buried, say, in the seabed at 1 meter burial depth. If you were to perform the current rating calculations simply in accordance with IEC 60287, you'd get a current rating of around 830 amps. And then if you perform for the same installation, same cable, but using the new C-grade technical brochure 908 armor loss calculations, and a more accurate, less conservative method, you could see an improved current rating at 920 amps. in detail, if you look at that in detail, so you've got the losses are in the table below. You'll see increased conductor losses for the TB908 method. That's simply because the conductor is actually carrying more current. So there's an overall increase in conductor losses. There is an overall increase in sheath losses. So what the technical brochure says is that uh, they actually think that the 1.5 multiplying factor for the sheath is not conservative. And so you'll see an overall increase in the sheath losses using the new method. But there's a significant reduction in armor losses, you can see, of almost 80% using this method. And then overall, we see an improvement in current rating of almost 10%. Let's talk about the critical sections for cable ampacity calculations for a typical offshore wind installation, which is, of course, a very typical application for these submarine power cables. So, probably starting with the most onerous, potentially is the landfall. So that's on the right hand side. You've got usually some directional drilling or an open trench in the landfall section between the uh, above the water level soil, and then moving into the seabed. Then we've got the J tube section. So for an offshore substation, these have J tubes. Also, each wind turbine has a J tube or multiple J tubes, depending. These are also a critical section which may be a bottleneck for the current rating. And then you've got to consider the current rating in the seabed. Uh, and that's another type of calculation. So typically what we do when we're designing or performing current rating calculations for this sort of installation is we break it up into sections and we consider the installation conditions at each of those sections, or you could say cross sections, and we perform calculations. And the section with the lowest rating typically dictates the conductor size for the installation. Let's talk about the design first before we talk about the modeling of the landfall sections. So as I mentioned, the landfall could be developed using horizontal directional drilling, or it could be, if that's not feasible, it could be an open cut trench. Typically, the deepest section or burial depth for a cable in these sections is 10 to 15 meters. You can see a cross section in the diagram there. The thermal resistivity of the soil at the landfall is typically higher than the seabed. It's also typically dry soil above the water table. And this is where soil drying out can occur as well, which can be cause a significant reduction in the current carrying capacity for the landfall. Therefore, the landfall can really be the bottleneck overall for the generation capacity of a wind farm, offshore wind farm I'm talking about. The ducts may be filled with a pumpable grout, and it's recommended that this pumpable grout does not get hard over time, or else it will be very difficult to remove the cables if necessary. And soil drying out above the water table, as I mentioned, the red circle there is a concern. HDD ducts, typically, it's recommended to have a diameter of those ducts of between 1.5 to 2.5 times the diameter of the cable, which is quite large. 200 millimeters internal diameter or larger. And another recommendation that you can use, remember that I mentioned that these submarine installations, solid bonding is used, and this can really derate the cables quite significantly. So if you need to get around that, and if the landfall section is a real bottleneck to the export cable to the installation, you can consider using single point bonding for the landfall section. And there is a paper mentioned in the notes on this page, which has used which has used a single point bonded section for the landfall, and that has improved the capacity of the wind farm significantly by reducing the losses for that section. Okay, we still have people joining. Let's talk about the modeling uh, now of the landfall sections. So the depth of burial is really, really important. So is the soil thermal resistivity. I won't be letting anyone further in at this point. So those are really important inputs to the calculations. You need to be able to model sections, the buried sections at different depths, and you may consider at the different depths uh, whether those whether it's likely that the duct is going to be filled with water, or it's air filled, or it's going to have a solid fill, like a pumpable bentonite or something like that. You'll need to include that in the modeling and the calculations. If the cables are really deeply buried, which they are for the landfall, for the deeper sections, it's a good idea to calculate the soil temperature rather than assume a conservative value from the standard or something else. You can arrive at that can usually be really conservative if you just assume a high ambient soil temperature. And you should definitely consider soil drying above the water table for the landfall, and you'll need software to do that. And if you have a really complicated landfall section that may consist of a large pipe, where you have multiple export cables or multiple cables within the pipe, then you'll need to perform finite element calculations. Our software can do that. You can see the mesh plot there, and that's overlaid with the temperature plot. But that's really an advanced sort of calculation, most often not necessary for the landfall, but could be. The dynamic rating of these export cables is really quite important. So it's not a good idea to consider that the export cables are operating at full continuous rating all the time. You can take, because the export cable is buried, there is large or long time constants. There is high thermal inertia for these deeply buried cables. We can take advantage of that. Typically, these export cables for wind farms operate at 50 to 70% of their full rating or full capacity. So it's a better idea to consider the dynamic rating, to perform a dynamic rating calculation so that we can increase the capacity of these cables. And typically there's a real world example, almost 10% increase in the rating of these export cables at the landfall by considering the dynamic rating or the dynamic loading of these cables, and particularly the export cables. And to do that, we take wind data, we translate that into wind turbine output, and then from there we can perform the dynamic rating calculations. Let's talk about the J-tube sections. Designing these sections, these are open-ended J-shaped sections made from metal pipes. They are attached to the offshore unit, an offshore unit. The bell mouth is underwater. That's where the cable enters the J-tube that's underwater. So there's a water-filled section, and there's typically an air-filled section above the water level. The inner diameter should not be less than 2.5 times the cable outer diameter. Otherwise, it's going to be very difficult to pull the cable into the J-tube. The bending radius of the J-tube should not be less than 20 times the cable outer diameter. These are just general rules. You don't really want to break them, or you're going to have difficulty. And multiple tubes can be used, and there's some recommendations there. Let's talk about the modeling for the current rating calculation of cables, submarine power cables in a J-tube. There's no IEC standard for doing this calculation. We have developed an analytical approach based on heat transfer principles, heat transfer equations. It's the air-filled section above the water level, which is the most onerous because air has a relatively high thermal resistivity, the air gap. So it's really that section. Now that section above the water level is also exposed to solar radiation, and it's exposed to wind as well, and that can also be incorporated into the model. It's incorporated in our model. It's assumed that the airflow in the J-tube section is not circulating. You know that the water blocks the air-filled section at one end. Typically, the top is open, but there is no circulation of air, so that's also considered in the model. There are a few major factors, and let's look at those, how they impact the current rating for cables in a J-tube. Starting in the top right-hand side, the air-filled section length. So the length of the section above the water, whether that's 10 meters, 15 meters, 20 meters, etc., really has a significant impact. So you can see this plot. As you increase the length of the air-filled section above the water level, you get a significant reduction in the current capacity of the cable within the J-tube. In this example, around over 30% reduction, moving from 5 meters to 20 meters in length. Bottom right-hand corner, you've got a factor that causes moderate reduction in current capacity. That's the solar radiation or the exposure of the J-tube to direct solar radiation. Now, it's not assumed that the J-tube, because the J-tube is vertical, so you can imagine it's not assumed that the J-tube is always exposed, or the surface area of the J-tube is not exposed. Sorry, I should say 100% of the surface area of the J-tube is not exposed to direct solar radiation at any one time. We would assume that 50% at most is exposed to direct solar radiation. There is another factor value given there in an older paper of 32%, and they've given some reasons in that paper, but it's not 100%. Considering direct solar radiation exposure of the J-tube, you could expect a reduction in current rating of up to, in this case, almost 15%. And then on the left-hand side, this is a factor that has less of an effect, and that's wind speed. It's more conservative to assume that the air is outside the J-tube is not moving, so still air, and this is the condition when you have the lowest current rating. So you could assume that, or you could assume maybe a few meters per second, and this would have a minor effect on the current rating. However, it's relatively minor. In this case, it's over 10% reduction, or sorry, 10% increase in current rating when you assume there is some airflow around the J-tube, on the outside of the J-tube. There is also the tube diameter that does have an effect. I don't have a plot here for that. but you can use the software to work that out. The seabed section is also very important. Uh, so typically these submarine cables are directly buried in the seabed at a depth between 1 and 4 meters. Typically, it's around 2 meters. There needs to be a survey done of the soil, the seabed soil thermal resistivity, and that is typically done right along the route. So lots of tests that usually performed, not always. Surprisingly, you'd see that even on very large important projects, it's sometimes not done, and certainly not done enough, in my experience. But they should be performed. TR tests should be performed along the cable route. Typical soil resistivity of the sea, because these soils are saturated with water. Um, the thermal resistivity of these soils is not very high. Typical range is between 0.4 to 0.8, but you could see something as high as 1.4 if you have very high organic content within those soils. And the also an advantage of the seabed is that the soil temperatures are usually quite low, depending on the depth. However, I mentioned here that the soil seabed temperatures are also highly variable, and you should look at seabed temperatures over several years, using several years of data. But they're usually much lower. 5 degrees is much lower than what you'd see on the land, and this results in relatively higher current ratings for the seabed. This diagram here illustrates the current rating for the cable being installed either completely in water, that's on the left-hand side, through to being partially buried in the seabed. So from sitting on the seabed to being partially buried, through to being fully buried on the right-hand side in the green section of the curve. That's essentially an IEC buried calculation. So you can see we go from the left-hand side, we go something like 1250 amps in for a cable in the water, the same cable. And then we move to partially buried and we start to drop down depending on the burial ratio. But once it becomes fully buried, well, actually at the very right-hand side, we drop down to almost just above 800 amps. So we go from 1250 to 800 amps. It's a very big difference between cables that are installed in water, partially buried, or fully buried. I've added a note in the bottom right-hand corner. By the way, I should add that the models for these calculations, so being completely in water, it's a convection-based model. We have developed this model. You won't find this model in IEC standards. It's a different sort of thermal model. Also for partially buried, this is a convection model and a conduction model. We have developed these models ourselves. You won't find these in the IEC standard. But for directly buried, fully buried cables, we're using the IEC method. IEC 60287. In the bottom right-hand corner, I've just mentioned that perhaps in the future we should start to consider marine growth for cables that are installed on the seabed or fully in water, as it looks like marine growth could provide a significant insulating layer around the cable. That's not something we've done yet, but perhaps in the future. Underwater factors affecting ampacity. So this is for cables, so dynamic cable systems. These are a new technology that's emerging. We have all of these floating wind farms that are emerging now. This image in the top left-hand corner is courtesy of Prismium, who are developing these dynamic cables. So the cables are not really installed in the seabed. They're in the water, so these in-water calculations are quite useful. And these plots show the factors that affect the rating. So obviously being fully in water, the current ratings are going to be much higher compared to if the cables are buried in the seabed or partially buried or sitting on the seabed. Um, Actually, I should say buried in the seabed. Water temperature, bottom left-hand corner. Water temperature has a significant effect on the current rating. So if you move from the right-hand side, so higher water temperatures to the left, you will significantly increase the current rating of the cable when it's installed in a lower water temperatures. Then on the right-hand side, you have other factors which have less of an effect. Water velocity, you might want to consider still water, or if there's some continuous current that you can consider. This has a low to moderate effect on the current rating. And then bottom right-hand corner, salinity. We do consider salinity, whether the cables are installed in fresh water or salt water, highly saline water. It only really has a significant effect on the current rating if the water is highly saline. I'll briefly mention the environmental impact, this 2K criterion, which is prominent, as I understand it, in Germany and being adopted by other parts of the world. It's a little bit controversial. Some people don't really agree with it in the wind industry or the transmission industry. So this requirement is that the cables that are buried in the seabed should not cause a temperature rise in the shallow area of the seabed up to 300 millimeters. They should not cause a temperature rise of greater than 2 degrees Celsius or Kelvin. This is quite a significant um, requirement. It can reduce the current capacity of the cable significantly. Obviously, it's affected by burial depth. So if you bury the cables deep enough in the seabed, obviously at a significantly higher cost, you will meet this. It's more likely that you'll meet this requirement. But in this example here, we've got a HVDC cable system buried at 1.5 meters. Now, on the left-hand plot, you've got if that circuit was running at its steady state capacity, it could be rated at 2035 amperes. But to meet this 2K criterion, such that the shallow soil layers are not the temperature of those layers are not increased above ambient by more than 2 degrees, this 2K criterion, we would have to reduce the current rating of these HVDC circuit by almost 500 amperes. So it's a significant reduction to meet this requirement. Right now, I'm going to hand over to Edston, and he's going to give a live demonstration of submarine cables, submarine installations, and J-tubes. And after that, we will do a live Q&A. I will also now share in the chat a link where you can go to a form and fill out your name and email, etc., to request a certificate to be sent to your email. I'll hand it over to Edston now. Thank you.
Thanks, Jason. Jason, I've sent a request to.
Hang on. Yes. Okay. I will share the link in the chat. Thanks, Edson. I'll leave it to you. And then we'll do the Q&A.
Yeah, thanks, Jason. If my screen is visible.
It is, yep.
Yeah. All right. So this is our software. ELEK cable HP. We are running on version 7.5. We have many installations, as you see on the top corner, starting from in-air up to FEM. We have specialized modules for crossings, magnetic transients, etc. Now, as Jason pointed out, the basic thing that we always do is model a cable. So when we model a cable, for example, I have two cable models which I have populated from our database. We have a database of around 1,000 cables and still growing. So from that, I've picked up two cables which are TB880 cases. One is a 400 kV submarine cable, which is a three-core cable. The other one is, sorry, 400 kV is a single core and 30 kV is a multi-core. Just to show you those cables, this is the single core cable having a screen sheet as well as an armor. We have multiple custom layers which are shown in the yellow colors here, and all parameters can be customizable depending upon the user data sheet. So we just scroll through all the materials and just input the data that's required for each of these materials. Similarly, if we go to the multi-core cable, again, similar, we have many custom layers. This is a cable with a sheath around a core and also an armor around it. So we can use for this cable, we could use the TB908 if required to model this cable. So again, we could go through each of these models and look at parameters of each of these layers here. Now we can use any of them in the study. So for example, here I have taken the submarine installation. The ambient temperature is 10 degrees of the water. Velocity is 0.2 meter per second. It's a seawater. And so I have water salinity. I can have fresh water too. And then I model my cables as equally spaced at 0.4 meter spacing between the cables. They are lying on the seabed. And the current rating I get is almost 1,590 amperes. Now I can change, as Jason told you, ambient temperature has a marked effect on the cable rating. So if I change from 10 to 15, the ambient temperature, my current rating will decrease to 1537.7. So there are instantaneous calculations that happen in the backend. So any parameters that change the front end would have an effect on the backend. So this is one type of installation to do. There was a question in the chat, if we have multiple soil thermal registries, what can be a method to do it? So what we have is like something like this. We have multiple sections here. So we have another section here where I have put the same cables, but they are partially buried. They are buried at 90%. So the current rating now is 1405 amperes. I can change the burial percentage, for example, to 10%. So it comes more into the water. And then we can see that the current rating has significantly improved. This is because of water convection properties that we use. So between buried and in water, we have massive differences. The other type of installation, again, what I can show is we could have cables completely in water. So this is a single core cable which is completely in water. We have the three core cable which is directly buried at 1 meter. So if you see here, the ratings for each of the cables are shown here. For the first circuit, which is the multi-core cable, I have a 737 amps. For the second circuit in water, which I have 1,509 amps. So we could do this type of installation. Even these installations which are partially buried, I can drag them to anywhere I want to get the in water ratings of these cables. So it's all drag and drop if required. Another extension of what we have done is having ducts in these cables. So this complex setup shows a multi-core cable in duct, which is in water. The cable is in the seabed, again in ducts, and then there's a directly buried multi-core cable. The ducts can support all the types of ducts that we have commonly used. You can fill it with air, water, or solid duct filling materials, and you would have your current ratings for all these installations. So this is another capability that we can do. We can do it in unequally loaded, equally loaded, or isolated ratings also. Finally, we have our J-tube section here. So in the J-tube section, again, air temperature, wind speed, water temperature, water velocity, etc. is considered. So you can have risers or J-tubes. The ones on the right columns are the J-tubes. The ones before that are risers. We could have different configuration of risers such as open, closed, open one and closed to the other end, etc. You would see that as we change, the current ratings also will change here. If it is in case exposed to solar radiation, we have a solar radiation calculator here. For example, it's calculating in France. We can do it in Sydney if required, and then it will populate the values here of solar radiation for a particular day or a set of days. So here I've done from 13th to 14th. I can choose any day for a year. If you want, you can take a year, and then we will populate the maximum value here, and then you can use it for your calculations. So this is another important module of our software. So with all these modules like buried risers and submarines, you are able to model a full section of the submarine cables as Jason showed you. So I think I'll just wind up this here. Uh, I'll hand it over to Jason to continue the presentation.
Okay,
Yeah,
so there's been quite a number of questions in the chat. Lots of questions. I've answered a
yeah,
few.
yeah. Okay,
You've answered quite a few.
yeah,
Um, I've also shared the link in the chat to where you can request the attendance certificate, so you can get the points. Um,
yeah.
so Edson, shall we answer a few good questions?
Yes, yes. Let me bring that up.
How I'll just answer this one. How are HDD sections modeled? Well, HDD sections can be just modeled simply. Are you okay? Let me share my screen. Let me share my screen,
Yeah.
and we will answer some questions. Okay, okay. It's then. So
Yes.
How are HDD sections modeled? HDD sections can be simply modeled as buried in ducts. If they are, however, quite complex, if you have ducts within pipes, multiple ducts, then you need to use FEM, the finite element method, because IEC won't be able to do that. We can
Yeah.
do either in our software.
Yeah, and just to add to it, I mean, we are coming up with a new method for HDD,
Mm,
uh, for multiple soil layers having different soil resistivities, different depths. We are coming up with a new algorithm for it. Probably in the coming releases, we will have it, Jason. Yeah.
yep, yep. Based on the conformal mapping, right?
Yes.
Yep,
Yes.
yep.
Yeah. Okay. So, a question that can be asked is like, what's asked is like, what happens to soil dry out in the seabed? Is it a possibility that soil will dry out in the seabed?
I mean, I don't think so. But again, that's an engineering judgment that you need to make. No one can say for sure. But if you think it's a possibility for whatever reason, then you as the engineer need to consider it.
The other question is, do we get a preference from clients whether to use the TB908 method or stick with TB880?
Uh, I mean, it's a great method. It's a validated method. It's current best practices. It's going to provide an advantage to your clients. You can turn it on or off. You can show them the result, and you can provide the technical brochure and explain why it's valid and why it should be used. I think you can easily answer that. I would recommend
And
you do use it.
yeah,
Certainly all the cable manufacturers are using it, so I would be using it.
yeah. Um, the other question is regarding the survey for soil thermal resistivity in the seabed.
Hmm.
Um, should that be done? Is that important?
Oh yeah, it's very, very important and it's usually done at lots of different sections along the seabed. I think there was a question there like how frequent should it be done? That's hard to say. But there is a good technical brochure on it by Seagray.
Um,
I don't remember the number.
okay, so the other question is, I think the impact of marine growth. I think you touched that on your presentation.
Yeah,
Could we add any assumptions to it?
it's not something, could we add any assumptions? I mean, you could possibly in the cable model add like an additional insulating layer and give it some thermal resistivity. That's a possibility if you really wanted to do it. I've not heard of it being done. I just think it's something that we should be considering. But I suppose it only really applies to cables that are fully in water, which already have a high current rating. Perhaps that would reduce the current rating somewhat so that that was more close to even a buried cable buried in the seabed. I don't know, but it's an interesting thing to investigate.
The last question, Jason, for today, we can do we allow hybrid armor types, and how can that be modeled?
Hybrid armor types, as in,
Yeah,
like they
as in
mean,
multiple materials for the same armor.
so that means like with like plastic fillers. Uh,
Yeah, yeah, yeah.
uh-huh. Um, I think what like a an insulating we don't as such. I think it wouldn't we could adjust the armor, the number of metal wires, and then I think that would more or less be fairly accurate. And then there's the insulating. If you're talking about insulating wires in between the metal wires, we don't handle that directly at present.
Yeah. I think there's one last question. How to model pressurized fluid filled or cooled HV cables? I assume it's pipe type cables.
Uh-huh. Yeah, it's then we can model
Yeah,
pipe
we
type
can. Yeah,
cables.
we can do pipe type cables. Yeah, yeah, we can do pipe type cables. Even TB880 has two examples of pipe type cables with I think it's low pressure oil filled cables. Yeah, we can do that in our software currently.
We can do all those cables, including
Yeah.
in FEM as well.
Yes, yes. Okay, yeah.
Yeah.
We'll wind up, Jason.
Fantastic. It's been a great presentation. Thanks everyone for attending. Thank you for your time. It's great to have you again. There'll be more of these, I believe, in around 3 weeks' time. We'll have another one, and I'm looking forward to seeing you then. Thanks, Edston.
Thank
Thanks,
you, everyone.
everyone.
Thank you.
Thanks. Thanks for your time, guys. See you again.
See you. Thank you. Bye.